Okay, everybody, I'm going to try this and we'll see how it goes. I'm going to go over the Chapter 16 test that you guys just took, and I'm going to do this over the internet so that we don't have to take class time and you can focus on the questions that only you need. Number one, which one is a Bronsted-Lowry acid? Remember, a Bronsted-Lowry acid is anything that could be a proton donor. And as I look at this, I see lots of places where you could have a proton donor. So the best answer here for number one is E. Second question, the molar concentration of hydroxide ion in pure water. That's just a question basically making sure that you know what you're talking about in terms of the H plus times the OH minus concentration always equaling out to H plus OH minus always equaling out to 1 times 10 to the negative 14th. And so if it's pure water, we know that these two are going to be the same thing. So you end up with an expression x squared equals 1 times 10 to the negative 14th. And you do a little quick math, and the best answer there is going to be D. 3, magnitude of Kw. Kw is a very small number, 1 times 10 to the negative 14th, which means that water auto-ionizes to a very small extent. It doesn't tell you anything about the speed with which it auto-ionizes. It does tell you that it doesn't auto-ionize very much. All right, continuing along, numbers 4 and 5. I underlined hydroxide in 4 and hydronium in 5 because when you see a high concentration of hydroxide, that means that you're talking about something that's acidic. And we know acids have really low pHs. So I'm looking for an answer here. Oh, excuse me, I said that backwards. When I'm looking for hydroxides, hydroxides are OH minuses, which means if I have lots of OH minus, I'm not going to have much H plus. Therefore, my pH, I'm going to be very basic, and I'm going to have a high pH. So the best answer there is B for number 4 for hydroxide. And in number 5, which solution has the highest concentration of hydronium? Hydronium, now we're talking H plus. Lots of H plus means lots of acidity, which means I'm looking for the lowest pH. I'm going with number 5 is A. Number 6, nitric acid is a strong acid. This means that we know that strong acids, their main important characteristic is that they dissociate completely into H plus and NO3 minus. So the best answer here for number 6 is C. All right, so there's the first page, and we'll continue on to the second page. All right, and in number 7, what are we looking at here? Which one of these is the weakest acid? Okay, think about this. Weak acids are going to not make lots of hydroniums and the conjugate base anion that would form when each of these are put in aqueous solution. So because I'm not forming, and if we just do a general sort of weak acid HA in equilibrium with H plus and A minus, we know that we'd be able to write a K expression, a Ka value, and we would be looking at concentration of H plus, concentration of A minus, all over concentration of my weak acid. Well, if it's a weak acid, I'm not expecting much H plus, which would make my Ka values very small. And so the weakest acid is going to be the one with the smallest Ka value. And once I remember that, the best answer for that is going to be D, HCN, because the Ka value there is just 4.9 times 10 to the negative 10th. All right, continuing on here, we've got number 8. We get the Ka of hypochlorous acid, and it's wanting to get percent ionization. So the tricky part here, kind of a two-parter. Let's go ahead and figure out, using the Ka value and the concentration, we write this as a weak acid equilibrium, H plus, ClO minus. We think about some icebox type of thinking here, and we're going to go with 0.015. We're going to subtract x. We're going to have 0 and 0. We're going to be adding x and adding x. And this just shows up again and again and again in these types of acid-base problems. And so then we can write the expression Ka is equal to x squared over 0.015 minus x. And now it's really just a math problem in terms of figuring out what x is. I'm going to take 3 times 10 to the negative 8th equals x squared over 0.015 minus x. Now this is a good example of where we can get away with using an approximation, because 3 times 10 to the negative 8th is an incredibly small number, and especially when we compare it to 0.015. So when we do this math, we're going to get 3 times 10 to the negative 8th times 0.015, and then we take the square root of that, and I'm getting 2.12 times 10 to the negative 5th. 2.12 times 10 to the negative 5th, and so that is telling me what x is. And so that's how much hydronium and ClO minus were formed. Percent ionization, then, you just have to remember, is we're going to take the amount of H plus hydronium ion formed, and we're going to divide it by the original concentration of the solution from which it came. So if I'm doing that correctly, I'm going to take the 2.12 times 10 to the negative 5th. I'm going to divide that by 0.015, and I'm going to remember that to turn that into a percentage, we're going to multiply it by 100. So we do all that math here, and let me see if I can get that done real quick. And I'm getting something on the order of about 14%. Which does not appear to be right. Oh, that's because it's not 14, it's 0.14. Mr. Caldwell goofed that up on his calculator. So the answer there was D. Okay, numbers 9 and 10, you had to remember what your strong acids and weak acids are. Remember that there were 8. And at the end of the day here, we ended up with a weak acid here, a strong acid here, and a weak acid here. You got to know your 8 strong acids. So the best answer for number 9 is E. And in number 10, you're going to be looking at a weak, strong, and the answer here is A. All right, continuing on. Number 11. If I get a problem that looks like this, I'm getting a molarity and I've got a pH. We just have to remember that pH is the negative log of the concentration of my hydronium ion. And so we can then say, okay, if that's 2.46, the way that you work this is you remember that logarithms are basically just exponents. So I'm saying that the negative of the exponent, so 10 to the negative 2.46, is going to give me the concentration of H3O plus. And so if I do all of that stuff, I'm going to get that 10 to the negative 2.46 power is about 0.003467, which is really close to 0.0035. And I really liked this question because what this forces you to do is forces you to recognize that if I have a 0.0035 molar solution and it looks like it's an acid because the pH is 2.46, well, what do I know about strong acids? Well, strong acids completely dissociate. So if I have a 0.0035 molar acid and I get 0.0035 molar of hydronium, that must mean that the hydronium completely dissociated from what must have been a strong acid. So the best answer there for number 11 was C. Hopefully you guys are sticking through here and getting the things that you need as far as questions that you had so far. All right, continuing along here, let's look at number 12. All right, and it says, using the data in the table, which of the conjugate acids below is the weakest acid? All right, so what we've got to remember is that there's a relationship between the Ka and the Kb of an acid and a conjugate base, or a base and its conjugate acid, that these products are always going to equal out to 1 times 10 to the negative 14th. That's a handy little thing to remember. So at the end of the day, if I'm looking for the weakest acid think back. I'm going to be thinking about really, really, really small Ka values. That's what I want to look for. Now, where would I get a small Ka value? Because Ka times Kb is a constant. The bigger the Kb, the smaller the Ka has to be. So if I look here, I see a very large Kb right here, which means that the conjugate acid of NH2CH3, and if I think about this, if this is a base, well, give it an H plus, then it would turn into the NH3CH3 plus 1. This is going to be the weakest acid, all right? So in number 12, we're looking at D, because that's going to have the smallest Ka based on the relationship here. Big Kb, small Ka. Continuing, number 13, of the following substances, aqueous solution will form basic solutions. So you have to remember how we play this game. You look at these, and these are all salts. And what you then presume is, let's look at NaHS as an example. NaHS would theoretically break apart into Na plus and HS minus when in aqueous solution. Na plus could be considered to have come from a strong hydroxide, the sodium hydroxide, and a strong base, sodium hydroxide. A strong base is going to have Na plus as a very, very, very weak conjugate acid. So weak that we wouldn't even consider it as an acidic ion. On the other hand, HS minus, all right, that's not coming from any strong acid. H2S, that's not going to be a strong acid. So it's a weak acid, so it's a reasonably strong conjugate base. And because of that, NaHS on its own is going to be a basic solution because of the presence of that HS minus, which is a reasonably strong conjugate base because it's coming from a weak acid. So at this point, we recognize that NaHS is basic. And so we know that it's either this or this or this. You go through and you play the same game with all of these others. And what you find out is that there are several here. The KHCO3 and the NaF are both going to be basic as well. F minus coming from HF, which is a weak acid, which makes the F minus a reasonably strong conjugate base. Na, same reason that it is irrelevant because that could be coming from a strong base, sodium hydroxide. We eliminate the K here. KOH is a strong base, potassium hydroxide. And then the HCO3 minus coming from a weak acid, so this is a reasonably strong conjugate base. We look at the copper nitrate. NO3 could be potentially coming from nitric acid. Nitric acid is strong, makes this a very relatively weak conjugate base. Copper hydroxide would be a weak base, so this could be a strong conjugate acid. So if anything here, we would be expecting this one to be acidic. So the best answer here would be these three. So for 13, the answer is E. In number 14, I'm looking for which of these compounds are going to be having a pH of 7. So I'm really looking for things, ions that are coming from strong acids and strong bases. I eliminate NaOCl because OCl minus is not coming from a strong acid. KCl, strong. So that one looks like a promising choice. And as I review the other ones here, I can eliminate these because ammonium hydroxide, definitely not a strong base. And while the calcium hydroxide might be, this OAC doesn't look like it's coming from a strong acid at all. So KCl here for number 14 is the best answer. Continuing, number 15, of the compounds, 0.1 molar aqueous solution will have the highest pH. Lots of thinking here. So what we're going to do is we're going to say, and I'll just tell you that the answer right here is A. And let's think about how we get to this, all right? If I end up with some Ka values, all right, let's focus on these guys. I've got Ka, Ka, and Ka. Now, you can look at these things and you don't want to get tripped up and say, oh, well, here's the biggest Ka, so this must be the answer. You got to remember that relationship, that Ka times Kb, when we're talking about acids and conjugate bases or bases and conjugate acids, that product is 1 times 10 to the negative 14th. And then you say, well, all right, so if I have a small Ka value, all right, what I'm really trying to do is I'm trying to figure out these aqueous solutions, which will have the highest pH, right? So you got to really think about that. If I want high pH, that's really the thing that's going to be kind of most basic. So if I'm going to be really, really basic, I want big KBs. So where am I going to get a big KB from? Well, these are Ka values. And if I have a big Ka, I'm going to have a really small Kb. When I have a really small Ka, I'm going to get a really big Kb. And if I have a really big Kb, that means that it's going to be a pretty good base. And when I look at KCN, don't get thrown off here. All right, KCN, the part that I'm most interested in is the Cn minus. That is the conjugate base of my weak acid HCN. So this one really comes down to just remembering this relationship and then being slick about thinking about if it's a high pH, you're looking for the most basic, which would mean the biggest Kb value. And if we do the math here, I believe we get a Kb that is bigger than either of the KBs here. And actually that wouldn't even make sense because these KBs, you're ending up with things that are acting like acids over here. So we can actually eliminate those from the consideration. All right, number 16. And I think I'm gonna have to do this video in a couple of parts here because it's getting kind of late. So I think I'll just get a couple more of these done here and then I'll put another installation up on YouTube here as soon as I get a moment. All right, so what's the POH? We continue along here, aqueous solution. So what do we know? We know that the concentration of H plus times the concentration of OH minus at 25 degrees Celsius is always 1 times 10 to the negative 14th. So in this case, I'm just reminding you, hey, you got to remember how to do these types of problems. And so we should be able to calculate this by doing some algebra. And I'm going to double check myself here. 1 times 10 to the negative 14th divided by 0.0025. And let's just hope that I'm getting the right answer here. I'm getting 4 times 10 to the negative 12th. All right. And so once I know that, we then remember, well, what did the question ask? It wanted the POH. So I have to take the negative log of 4 times 10 to the negative 12th. Sorry for the shadow there. And if I go negative log of that, I'm getting 11.40. And there's no such thing as a negative here. So we're going to go with B as the best answer for number 16. Why don't we do one more here? Let's see. You know what? I think I can get 2 or 3 more and then we'll call it a night. What's the concentration of hydronium ions? So right out of the gate, I'm giving you pH. And so what I'm going to say is pH. I'm going to take 10 to the negative 4.153, and that's going to give me the concentration of hydronium ions. And when I do 10 to the negative 4.153, I'm getting about 7.03 times 10 to the negative 5th, which is D. 7.03 times 10 to the negative 5th. Number 18, what's the pH of a 0.035 molar aqueous solution of barium hydroxide? Barium hydroxide, you remember that barium hydroxide is one of our strong bases. All of our strong bases are the alkali metal hydroxides and the heavy alkaline earth metal hydroxides. So because it's a strong base, it's going to completely dissociate, which means that I'm going to end up with 0.035 molar, and be careful, OH minus. And so at that point, I can figure my POH, which is negative log concentration of hydroxide, which in this case is 0.035. And so I get a POH value when I plug that into my calculator. So the negative log of 0.035. And then you have to remember a nifty little fact. pOH here is 1.456, taking it to probably one extra decimal place there than I need. We have to remember that pH plus pOH is equal to 14. So at that point, I can basically take 14 minus my 1.456 number, and I'm getting about 12.54, and that is what the answer is here for 18B. 12.54 is the pH. That's an easy place for folks to make mistakes. And let's go ahead and do 19. Which is the weakest acid? We talked about this in class, and we basically said that because oxygen is a very electronegative element, the more oxygens that are present, and you have HI and just more oxygens, depending on which choice you're looking at, the more oxygens present, because there's more oxygens, there's more electronegativity. The oxygens hold on to the electrons more intensely, making the hydrogen feel, in essence, more and more like a bare naked proton. And if I'm a bare naked proton and a water molecule happens to go by, I may just donate myself and form hydronium. So the more oxygens, the stronger the acid would be, which means if I'm looking for the weakest acid, I'm looking for the one with the least oxygen. So I'm going to go with A for 19. All right, number 20. What's the conjugate acid of CO3 2-? Well, let's see here. The conjugate acid. So that means that I want CO3 2- to act as a base. And a base, when in the presence of water, is going to be a proton acceptor. So if I visualize an H plus peeling off, I'm going to end up with HCO3, not 2-, but now 1-, and an OH-, because bases increase the concentration of hydroxide when added to water. So the conjugate acid of CO3 2- would be what results when it absorbs that H plus that was stripped off. And so I'm looking for HCO3 with a -1 charge. Make sure you're careful on the charge there. So number 20 is D. And we'll go ahead and finish this page. The conjugate base of H2PO4-. So we want to think about H2PO4- now acting as an acid because we want to find its conjugate base. So acids donate protons. So I'm going to form a hydronium. And what's going to be left when I peel an H off of this? It's going to be HPO4. And if I've lost an H, I'm now going to be at 2-. And so that corresponds to answer D for 21. That's probably enough for tonight. I'll make another video and finish this up here and send the link to you. All righty.